Hello, so today we're going to be doing Dijkstra's algorithm. So the goal of Dijkstra's algorithm is you can pick any node on the graph and you're able to find the shortest distance between other nodes. For example, let's say we pick A, we're able to find the shortest distance to B. Pick E, we can find the shortest distance to A. So we can find the shortest distance from A to E, A to B, A to C, A to D. But let's say we choose D, we will be able to find the shortest distance from D to C, D to E, D to A, D to B. But let's assume that we choose A as our start state. So this is our start. And our goal, again, is to find the shortest distance between each node from A. And we're going to have a set for visited, so we don't repeat going back to nodes. And we're going to have a table that keeps the shortest distance between each node and also the previous node. So obviously, from A to itself is going to be 0. And the previous node is just itself, but we don't have to mark it. And we look at its neighbors. So we currently have infinity signs initially. And basically our goal is to fill out this infinity sign. So we want to replace the infinity sign if the value is less than it. So for example, A to B is 7. 7 is less than infinity, obviously. So we can replace infinity with 7. And for E, we have 1, A to E. And E, we have infinity. So 1 is less than infinity. So we can put 1 there. And we have previous nodes, which is A. So now what we do is we want to pick the shortest distance from the list that's not visited yet. And A is already going to be visited. So we can put A here and add A to our visited set. So we won't bother with that. And the shortest distance in this list is obviously going to be E, which is 1. So we can mark out A, and now we're going to be at E. So now that we're at E, we're going to have a cumulative cost of 1. So it's going to be 1 plus whatever its neighbor's weight is at. So for E, we have 4 neighbors, which is A, B, C, and D. But A is already visited, so we don't bother with that. So let's go E to B. It's going to be 1 plus 8. And that's 9. And obviously for B, the value is 7 right now. But 9 is greater than 7. So you don't need to actually replace this value. And that's the biggest thing because we want to find the shortest distance. So we don't do anything with that 9. We check E to C. We see it's going to be 1 plus 2, which is going to be 3. So C is 3 because 3 is less than infinity. Now we look at E to D. We have 1 plus 7, which is 8. And we see that 8 is less than infinity. We replace it. So we replace it with 8. And obviously you put E right here and you put E right here. Okay, so now that we're done with E, we can put it in our visited set. And based on this, we want to find the shortest distance on this list. And from that, you can see that we're going to visit C next. So at C, we're going to see it's going to be, C has 3 neighbors. And we visited E already, so we don't bother with that. So C to B, that's going to be 3. So 3 plus 3. We grab the value from the shortest distance on the table. So 3 plus 3 is 6. And you see the value of 6 is less than 7. So we can actually replace this. So let's replace it. So 6. And we update its previous node, which is C. So now we're done with B. We don't need to do E. We look at D. So we have 3 plus 6, which is going to be 9. So is 9 less than 8 on our table? No, it's not. So since it's not, you don't update it and do anything with it. So now we are done with C. We can update our table and mark it as we're done. And based on this, what is the lowest value between these two? We see that it's going to be B. So let's actually mark out C right here, and we're done with that. So on this table, we have 6 and 8, and a B and D. B is the smallest value, so we move on to B. See, so you can see that we already marked out all of its neighbors. We already finished with A, we already finished with E, we already finished with C from B. So since we're done with that, we can just finish there. So we're done over there. And now we're going to be at D. So from D, obviously, when you add the value of 8 plus whatever here, it's going to be greater than the other values. So we can just finish off here as well. So we're done with our visited set. We visited everything. Everything's visited. Now from this table, you're able to reference the shortest distance from A to any other node. So for example, if you want to get to B, you would think we would take this A to B path that's going to be 7, right? But there's actually a shorter path. So if you look at this list, we can go to C. So this is going to be A to B, right? So this is A to B. You can go to C. You can look at C. You can go to E. So E. And then from E, you can go to A. And you can see that this is the shortest distance. And we can also add its weights on here. To add its weight, we'll just do 1 for E to C. E to C is 2. C to B. C to B is 3. So you can see that this is the shortest distance to get there. And from B, you can see that B connects to C. We already finished that. Now let's look at D. D is connected to E. So that's this previous node. And from D to E, we said we had the value of 6. So yeah, you can basically kind of see that we were able to actually fill out this table. And these are currently the shortest distance. Really, you don't have to draw out this graph. You can just have it simplified like this table right here. So if you were to answer this from A to B, we know the shortest distance is 6, A to C. We know the shortest distance is 3, A to D. We know the shortest distance is 8, A to E. We know the shortest distance is 1. And yeah, we're done with this problem.